Okay, hello everyone, welcome to my talk, bringing Frostbite to live service. I think it's probably best to start at the top. So who am I and why am I talking about this? Well, my name is Lewis Strudwick and I'm a Director of Architecture for the Frostbite engine at EA. And if you're unfamiliar with Frostbite, here's a set of titles that are all powered by Frostbite. And as you can see, they cover kind of different genres and different styles of games. And, that doesn't really explain why I'm talking about live service. And to get a better idea of that, if we bring up a map and we kind of superimpose the locations of the Frostbite studios on it, you can see that Frostbite's a global team. And the majority of the developers are in Canada and Stockholm. But down the bottom, in sunny Melbourne, there is a group of us here. And you might be starting to work out the coincidence here, because we're actually co-located with another EA studio in Melbourne, Fire Monkeys. Now, Fire Monkeys is an EA mobile studio that has been developing games here since its inception. And in a previous life, I used to be the engine and central tech lead for Fire Monkeys. So I have a kind of sort of more of a mobile background, and one of the things that was very formative for me was that I actually joined mobile early enough to kind of watch the games that we produced and the requirements change. So when I joined, you actually could quite reasonably expect to spend $10 or in Australian money like $14.99 on a mobile game, and that's fine. Yeah, it seems kind of crazy now, but shortly after that, Apple introduced in-app purchases. We kind of had Angry Birds' sort of last hurrah of the premium games. And then from then onwards, like the free-to-play business model just dominated. And you can see down the bottom, The Sims FreePlay and Real Racing 3 are two of the kind of most long-lasting Fire Monkeys games that I worked on. So, just so we kind of can still establish this sort of setup, this talk isn't actually about mobile games, and it's not about business models or anything like that. But I think there's a lot we can learn from the technology of mobile games and kind of how the business actually works, the business of developing them works. And I think it's also worth saying that this isn't strictly a talk about Frostbite either. I'm using Frostbite as a kind of framing and to provide context. But really, a lot of what I'm talking about can be applied to any engine. So, just a quick disclaimer, a lot of what I'm talking about with Frostbite is kind of in progress or in design. This isn't really a kind of retrospective talk, and it's not a discussion about strategy. These are just my opinions. But it is something that we think about, or at least I think about. So now that's over with, let's kind of start at the real kind of root part of this conversation. Like, what is live service? What is a live service game? I think a lot of people have a different set of ideas when I say that, and these are all live service games. Maybe they don't all match your idea of what a live service game is, and Apex is a free-to-play shooter. That seems like an obvious live service game. Battlefield 5 had very extensive post-launch support. Anthem was very ambitious, and they were really going for like fully integrated online services. And Madden, maybe that doesn't seem like a live service game, but they have seasonal updates, they have to keep things fresh, and they have a big kind of post-release plan. So what is a live service game, and what do we mean by live service? Well, I think the key thing here is that a live service game is one which is designed to keep the players engaged for some indeterminate amount of time. And the reason for that could be monetary. It could just be to keep them interested while they wait for something else to come up. It's hard to say. I'm kind of not casting aspersions on that. It doesn't really matter. It's sort of neither here nor there. The important thing is that to keep players engaged, we actually have to continue development. And that development will continue for as long as we need to keep the players engaged for. So with that kind of framing, what are the actual problems that we need to solve to support live service from a kind of technology perspective? So the first thing is new content. It's kind of the most obvious one, which is obviously if your game is going to continue evolving, you sort of expect to have new content produced all the time. And this content needs to be made to keep the players interested. And from my perspective, when I say content, I mean like it could be art, it could be design, it could be programming. You know, it's essentially anything that the players are consuming. A kind of more subtle version of new content is this idea of dynamic updates and dynamic content. So outside of our usual sort of patch release cycle and our kind of dev cycle, live service games often need to react kind of faster. Like one of the big examples, of course, it's like for any kind of live service game with an online component or a multiplayer component, you may need to do, say, balance and economy tweaks sort of that day. Like you have to respond to the player base as soon as possible. So we also have this idea of kind of dynamic content, which is sort of pushed outside of the usual patch release cycle and doesn't come with a new executable. That would be one of the kind of key distinctions. So what else needs to be solved? Well, and you know, this may be me showing my cards as someone in central technology, but you know, a live service game may have a very long lifetime, and if that's the case, they need to consider how they're going to deal with engine updates and technology updates in general. Especially for live service games that last multiple years, it's quite reasonable to expect that they will need to take engine updates, and actually managing that can be quite subtle and complicated. Something that's maybe less obvious to people is there is a kind of generalized production support requirement here, in that live service games are not produced, they're not built the same way that you would build a boxed product. And that's true even in the case where like you're running up to the release and then things change post-release. So I think it's important that the technology is kind of aware of that and sensitive to that, and kind of provides for changes in game team makeup. And you know, I think one of the key things is talking about multiple development groups in parallel, which I'll discuss in more detail later. Another thing that I think is interesting is user-generated content. Now, this is obviously a huge topic, and I'm beyond this slide. I don't really talk about this at all. But I think it's interesting because, firstly, obviously, UGC can create an incredible longevity for games. You know, it can provide the community with real kind of extra life in a game. And you know, like Skyrim was released the first time like 10 years ago. And you can see how things like their active community have made a big difference. And I think this actually relates to the production support, because one of the things that we see in live service is that it's very important to deal with kind of the reduced capacity of the production teams. For a whole pile of reasons, it's more important to empower each individual creator more. And this is what I feel is the case for user-generated content and modding as well. It's really important to be able to kind of support sort of individual creators as much as possible. So I think it's interesting to keep in mind, but you know, it's a whole technological discussion that is way beyond the scope of this conversation. So I think when we look at these problems, if you kind of really take a razor to it, there's actually only kind of two things that need to be solved. And the first one is about data management. So we need to find a way of kind of managing and integrating data in a kind of simple and intuitive way. And the tools need to support that. And that is both dynamic data and new content and, you know, all the kind of production up to that. And the next one is kind of the development flexibility, like how we actually produce that data maybe doesn't kind of fit the model that we would have previously in terms of just like box product development. And so the tools again need to be kind of sensitive to it, sympathetic to that kind of development process, and you know, we can't just treat it as if it's the same as box product. So, you know, I think that's sort of where I am at with the problem statements. So let's talk about something simple. Let's talk about the deployment of games and patching, which sounds like the easiest one, right? So in the old days, you would have the LD game. It would be on a CD-ROM or floppy disks if you're of an appropriate vintage. And it would have the executable and all of the content shipped. And the team would work up until ship date, and then it would be done. That would be it. And if the game was very successful, then some of the team might go on and build an expansion, or you might contract someone else to build an expansion. The rest of the team would kind of have moved on to the sequel or another project or something. And the expansion would also probably be distributed as another disc, and usually it comes with an executable that supersedes it. And sometimes it would even have, obviously it would have its own content, but sometimes it would actually incorporate the base game content because it's just easier to just package them together. And back in the old days, you had plenty of space on a CD. Now, that's not what it's like now. So nowadays, you have the whole team working up to produce the kind of the gone gold executable. And of course, once that happens and it's sent off for kind of certification and manufacturing, the team continues and they produce the real executable, the day zero patch. And this is the one that everyone plays. And I'm sure people who have played games in the last 10 years are familiar with the feeling of the day zero patch content also being approximately the same size as the game. And so, a lot of things happen in that intervening time, and then kind of following that, you probably expect to have some patches developed as the team starts peeling off and moving on to other things. But it's not just patches and dealing with patch content. You also probably have some kind of tweaks that are pushed by people monitoring the player base and seeing if there are any things that need to be turned on or off. DLC is likely to be developed, often lots of it. And I've also left some space on the side for this spooky server cloud component, where often there's an entirely different tech stack dealing with kind of online services, so like telemetry, multiplayer services like matchmaking, and also dealing with things like the economy and balance. And the server's going to have a bunch of content as well. And that's usually derived from the game content, but the server, it's usually using a different version of it, or like sort of parallel path for the content. And the thing that makes this extra complicated is that these are actually these are all maintained by different teams. You kind of have your main team working on the game and the patches, and then there's like a live team that's dealing with the kind of immediate responses, and they might be working on hotfixes. You'll have a server team, and then a team working on kind of expansions and DLCs. And these are all sort of being worked on in parallel. So I think that's a key thing. Like if you haven't worked in live service, it may seem that a live service game is kind of just a game with infinite expansion packs. Like, the team makes a game and then they make expansion pack 1 and then expansion pack 2 and they just keep going, right? But it doesn't work like that, because the complexity comes from the fact that there are actually multiple teams running in parallel. And those teams could be different disciplines. Like you could have just a small engineering team working on hotfixes. You might have a full dev team working on the next set of features. And you might have like teams of production and like producers and designers looking at things like economy and pushing changes or doing A/B tests or something and seeing how the player base reacts. And they all need to work in parallel. And crucially, their work is distributed to the players kind of independently of each other. Like, you don't wait for the feature team to be complete before you push an economy change, or hotfixes need to come out first. And this makes things complicated. So, when we start at the kind of the simple side of things, which is just like data deployment and patching, there's this kind of thing with live service where, patches are kind of are slightly more complex than they were before, and they were already complex. So just to kind of give people an idea of what we're dealing with here, when we deploy content that supersedes existing content, or we add additional content, we actually have to be really careful, because it can be extremely challenging to maintain things like performance characteristics. So, one of the things that we have to consider is that spinning disks are actually quite sort of slow at seeking, especially optical drives, but hard disks are also the same. And, we developed these kind of requirements based on what the market needed. So if you look to the side, this guy, the PS3, really drove a lot of engine decisions, certainly when it was new. So engines of the kind of vintage of Frostbite, they tend to be highly optimized for high latency media. And Frostbite is no exception. It's extremely highly optimized. It's one of our great strengths. And although not all engines are kind of built to this kind of set of requirements for Frostbite and for the things that we needed to do, we really pursued that. So, anyone can generalize, right? So let's talk about something specific. So if I'm trying to build an asset in Frostbite, I basically point the build system at an asset and I say, I want this build. And the first thing it does is it looks at all of the other assets that asset is referencing, and it grabs them as part of dependencies. And those assets could be, like, for example, you might be building a mesh. It could bring in a material, which could bring in a shader and a texture, all sorts of things like that. It basically gathers all of them up in a kind of big dependency graph. It then runs through a build system, which produces the kind of runtime version of the data. But then, crucially, it puts all of these together in something called a bundle. And the bundle basically is a single load unit. So when I load asset A, I know I need assets B, C, and D. So the bundle loads them all together as a sort of contiguous unit, and you just get everything together. And the bundles could be streamed, they could be all just loaded on demand. It doesn't really matter, but the point is, we know that all of that content is necessary. Now, this is obviously a highly simplified version of this, but let's say we've got, two things that we need to put together. So we've got two kind of assets. These are, in this case, sublevel 0 and sublevel 1. Maybe they're different streaming units. They're kind of independent of each other. So the implication is you don't necessarily need both of them at the same time. They might be both part of the same level or something. And we want to deploy them to the player. So we take these bundles and we put them through a tool which produces something called a super bundle. Now, the super bundle contains the internal bundles, and it doesn't de-optimize them. So keen-eyed viewers will have noticed that we've actually got some asset duplication in there. And the reason for that is that there are two bundles inside the super bundle, and we are simply, providing them both as independent load units. And that's why they're in the super bundle, and they're contiguous units. Now, kind of continuing this simplified version of this, when we deploy this to the player, we have kind of two options. We basically have this option where there's no seeking, everything's super fast to load, it's very efficient, but that could be an issue. Like, we're dealing with maybe gigabytes of textures, hundreds of thousands of assets. This can be a problem, right? So we have option 2, which is where we deduplicate all of the assets inside the super bundle, and we create a kind of catalog store. And this uses much less space, but it does actually impose a performance penalty. And in fact, every time we load either of those sublevels, we're going to need to do some seeking forwards and backwards to kind of find everything. And depending on exactly what the seeking strategy we use, that could be reasonably complicated. Now, apologies to anyone in Frostbite who sees this presentation, who works on this, because I'm massively simplifying this to the point of butchery. But we've experimented with both of these options in Frostbite, and actually the one that we choose is sort of somewhere in the middle, where we kind of deduplicate some things, but we optimize for seeks as well. But just so that you're aware. So this kind of deduplication seeking problem is kind of exemplified when we start looking at patches. And so traditional patches in Frostbite are called sidecar patches, and they kind of sit on the side, where you've got your super bundle, which is deployed potentially on a disk of some sort, and then your patch is downloaded to your hard drive. So with sidecar patches, essentially you have the deduplication problem in that you require seeking. And the more data that you put in the patch, the more seeking is required, because you'll have more and more assets referring to this sidecar instead of the super bundle. And this is where it kind of gets really perverse. You actually can end up with worse performance if you've installed the game from like a digital edition than you would have if you had a disk, even though the hard drive has better seeking behavior, because you might end up with two files on a hard drive and seeking between them, rather than having one file on disk and one file on the hard drive, which is quite surprising. So, continuing the theme of patching, like there are other options, right? So first-party console providers, they provide in the OS a kind of patching system, so we can actually do an in-place patch. So if we've got our super bundle, we can replace blocks inside it. But they don't give us kind of unlimited power. Basically, we can control individual blocks, which are usually 4 kilobyte aligned. But this is a kind of common scenario where, like, the new version of the game, the new version of the content, it's actually resulted in a size change. So in this case, asset C has increased in size by 1 chunk, and we've also modified D, but that hasn't changed size. And if you look at this, suddenly none of the blocks line up apart from the first one, because we've changed the size, and so the packing has changed and everything has flown over. So if you actually look at the kind of amount of data that we're downloading, you can see that even though we've only changed like a tiny fraction of the content, we've downloaded the majority of the data. And I think everyone has experienced the inexplicably huge patch scenario if they played any games. So this is what's happening, basically. So how can we fix this? Because, this is important when we're talking about kind of patching performance, especially when we're dealing with live service games where we expect to have lots and lots of patches. Well, we could pad things, so we can basically align everything to blocks. That solves a bunch of problems, but as you can see, we've increased the amount of storage space required by a significant amount. And again, when we're dealing with hundreds of thousands of assets, this adds up fast. So something we're doing for Frostbite now is we're actually trying something a little bit sneaky. We're essentially saying what we're going to do is we're going to preserve the relative offsets of every asset inside a block. So same scenario, we've increased the size of C, we've patched D. Now, we basically have to replace the whole block that contains C and D because it's now bigger. We do replace the block for D, but because we haven't reflown everything maintains its local offsets. What we actually have done here is we've just inserted a new block inside the middle, and we just replace the other parts appropriately. And so this is how new Frostbite games are going to be working. And this is particularly cool because we have a really nice trade-off between like the kind of the extra deployment size, which kind of grows as patches are required, rather than kind of shipping a really huge version of the unpacked version of binaries. And we keep our seek performance high, and we don't download as much. So the extra padding we can easily absorb at load time. It's not a lot of data. We can just discard it once it's loaded. And this is what all future Frostbite games will be doing, or a variant of this. So you might ask yourself, it's the year 2021 allegedly. Does seeking even matter anymore? Well, increasingly the answer is no, right? Certainly on mobile it was no, and as we start having more and more SSDs, it's less and less relevant. But unfortunately, not everyone has an SSD, and not all the consoles have SSDs. So we could be dealing with a situation where you're running on a 5400 RPM hard drive, which is like 50 megabytes a second contiguous read speed, or a PCIe Gen 4 SSD with hardware compression, which can hit 7 gigabytes a second. This is a 140 times performance delta. So it's something that's still very relevant. And not only that, but having good data layout gives you a kind of plenty of headroom when it comes to performance, and it also means we can control things like patch size and deployment size well. So it's something that we still consider. Okay, so I just said SSDs are on their way in and spinning disks are on the way out. So what about the idea of bundles? Do they need to stay around? And the thing is, bundles actually remain relevant. The idea of this kind of contiguous piece of data where all of the bytes are physically next to each other isn't so important anymore. But knowing what we need to load ahead of time, knowing dependencies, that is very important. Because, when we look at the latest generation consoles, they deal with a kind of system where you can service a huge number of asynchronous reads very, very efficiently, and they can hit those kind of 7 gigabyte per second numbers that I mentioned before. But we can only do that if we know what to read. And as soon as we introduce the CPU in the kind of middle, where we issue a read, wait for the result, and then determine what to read afterwards, that slows things down immensely. And so for us, bundles are kind of evolving from actually putting the content right next to each other to just having a sort of catalog and a directory of what we need to read and where. And having them scattered isn't so much of a concern anymore. But I think the key part here is that even though patching and dealing with patches in live service is very important, it's only one part of the problem. So the biggest issue is that for a live service game that has a kind of multi-year lifespan, you kind of expect content to go through some kind of structural change during that time. It's just unreasonable to expect it to remain static. So if you don't know what I'm referring to here, I mean something like this. So if you imagine this kind of made up inventory record structure, at some point later, maybe a year later, someone adds new features to this, and now we have a new field at the end. And that means that the sizes of all of the previous ones are now wrong, and so the content is now corrupted. Another one, which is my personal favorite example, is enumerations. They are always one of the sources of this concern, and in this situation, you've got your enum set up, someone adds a new field, and now what was previously invalid now has unexpected behavior. So, from the perspective of the code, like only one of these is right. It's whatever it was compiled with, and that's really key in terms of allowing us to do things like load and go formats, because the most efficient way to load data essentially is to bring it in from the disk, point to it in code, and say that is of this type, and then you can just read it as if it was deserialized into memory, and that allows us to do incredibly fast reads. But one of the issues with this is that it requires us to kind of refresh cold data. And by that, I mean data that hasn't actively changed. Like you haven't added a new feature, you haven't patched anything, you haven't changed any behavior. But because you have a new executable, suddenly you have to redeploy content that hasn't been touched. And just a short aside, because it's its own topic, managing this for safe games is extremely, extremely complicated. So it's a fun problem to have. So another thing that I think people don't realize when they kind of start to consider this kind of data mutation over time is that they sort of imagine it to be a backwards compatibility issue. You've got your code, which is running the latest version, and you might be dealing with older content. But actually, that's not the case. It is possible for you to end up with your code actually having a kind of an older idea of what the content could be, because you could imagine like a server providing the very latest format to clients, and your client code may be a little bit behind. And this sounds like some sort of tortured hypothetical example, but for mobile games this is a real thing because of the kind of rolling updates and the way that we manage CDNs. This comes up a lot, and it's a fun problem to have. So when we're dealing with live service, what about, let's just say, okay, what happens if we imagine that the code and the types within the code don't match what's on disk? What does that actually mean? Well, obviously we can have smaller patches. We don't have to refresh cold content, and it gives us more kind of flexibility. We could be distributing data of different vintages and kind of deal with it. But how do we deal with it? Well, we'd need some kind of load time fix-up, some kind of like in-place upgrade. And to even have a chance of doing that, we need to have full type information embedded. So, we need to know which version of the content we're looking at. And assumedly, there's also going to be some kind of performance hit, because you can't just do the kind of load and go thing. So for us, it's kind of good news, bad news situation. Like Frostbite actually already embeds all the type information that we could possibly need. Unfortunately, because of the way that the rest of the engine is set up, it kind of assumes that the content and the code matches. So there are lots of places in the code where we just don't bother trying to sort of validate against the on-disk format. And for us, we're really exploring how far to take this. And at the same time, we need to kind of get a good handle of what the actual costs will be. So, the first question, of course, is like, how much data are we actually talking about here? We're not talking about updating like the codec of textures or anything like that. This is a much smaller percentage of the content than we actually deploy. It's just a small fraction of it. It's what we would call kind of structured or gameplay data. So, does it actually limit performance? Like if we're only talking about a very small percentage of the data, does it limit performance in the real world? Does it stop us from issuing efficient loads? Thus far, we've kind of experimented with this, and it doesn't seem like it would. We now are really just asking ourselves, like, how far do we take it? Like, what sort of level of structural transformations are we going to be able to deal with? So for us, we're starting with what we call data resilience. And data resilience is kind of a collection of fundamental pieces. So we're dealing with simple things like renaming variables, remapping enums, resizing the sizes of structures. And, if you resize a structure, you've got to provide content there, so we need better default value handling. And the other thing, of course, we're doing is we're trying to make sure that parts of the engine that have previously assumed that these line up no longer make that assumption and go through the kind of correct APIs. So one of the things that we've done already, we did load time fix-ups for data offsets. So our script bytecode used to be compiled with the type information, and we used to kind of bake in like variable offsets for structures. Now we don't do that. We do a load time fix-up, and it made no difference to the performance. But now we can run scripts on different vintages of data. And for us, all of these kind of fall under a sort of low-cost, high-reward bucket. And they provide some really nice benefits. So there's another kind of set of problems that we have to deal with data, and I talked about this previously, is like dynamic content. So what about if we have content that we kind of know is going to be driven externally? And by that I mean things like economy balance changes, A/B tests are a good example, and any kind of time limited event. So this is something where someone is pressing a button on a server and deploying it. So I think the best thing to do here is to look at mobile and sort of see what we can learn from that. And one of the things that's most fundamental here is that you kind of have to expect these changes to be coming from a variety of sources and a variety of users, so different disciplines. So, they might be authoring the content in like Frostbite, or they might be authoring it in Excel. And the content may need to kind of bounce through an online tool that is doing aggregation and telemetry information as well. So it's very, very important for us to kind of expect that. And what we've seen in mobile as well is that it's not an efficiency bottleneck. Like a lot of this is sort of metagame stuff rather than kind of moment-to-moment gameplay. So, we can probably relax some of our requirements on performance here. And what we've seen in mobile, and certainly in FireMonkeys, is we invested in having a very flexible data format early on. And this was supported by the engine all the way through. And it made a huge, huge difference for us. It paid enormous dividends. And, we built big kind of ingestion systems that could take content from all sorts of places and whatever made sense, basically. And so, the thing is, like, for Frostbite, this is kind of, it's quite against the sort of inherent engine design philosophy that was baked into it. Because we sort of assume that we know everything at bake time, and we use that to optimize things like the runtime performance and the actual like bake time optimization, so we can determine exactly what we need at any given time. So the games that are using Frostbite that have had to solve this problem, they all have hand-rolled solutions, and those solutions tend to be quite sort of intrusive because they go against some of the inherent assumptions of the engine, and they're usually quite limited. So you will need an engineer to set up the data to be modified. Only particular types of data can be modified. It's quite sort of rigid in terms of what they can do, and it's different for different game teams. So for us in the engine team, what we're basically doing is we're saying there's an entirely new class of data, a whole new type of data that we're going to treat differently. And this data is sort of externally driven. And, we basically say, most data doesn't need this kind of set of capabilities. Most data is not externally driven. It may be patched, but we don't expect it to be downloaded on demand on startup. And for us, we're looking at how we rewrite kind of parts of our build and dependency scanning strategy, because we need to support this whole idea of having kind of soft references to this dynamic data where we kind of only realize the content when objects are reified. And they also need to be fully integrated into our tools. And in mobile, the game teams drove a lot of their tool integration, and in many ways we're trying to do the same thing here. We're looking at the tools that the studios have built and what different game teams have come up in terms of their solutions, and we want to make sure we can unify them all together and kind of provide a sort of generalized engine level support for this concept of dynamic data. And that's something that's still in progress now. So the next topic that I wanted to discuss was one of engine updates. So again, I'm from Central Technology. This is obviously one of my axes to grind, but I think it's important. When you're going into a game team, you're working on a live service game. How long is your game going to last? When we worked on The Sims Replay, we thought if it was successful, maybe a year. Outside estimate, maybe 3 years. It's approaching its 10th year now, And I think the thing that's important, and the thing that I've internalized from mobile, is that you can't assume it will ever end. Basically, if you're working on a successful free-to-play title or a successful live service title, you could be there indefinitely. And that's not a bad thing or anything, but it does mean that you have to kind of remain a good citizen from a technology perspective. You should be taking sort of engine updates, especially if you have any kind of centralized technology group that can potentially support you. And this is something that's really challenging for game teams, because from a kind of risk assessment perspective, this can seem like an unnecessary risk for kind of amorphous possible benefits in the future. But I'm here from an engine team saying, these costs add up, and you might think, why would I need an engine update? Well, you might just need new features. So in mobile, we had an interesting experience where someone decided to cut a big notch out of a screen on a phone, a fairly popular one, and then all of our UI systems had to be updated, and these were quite kind of fundamental changes. And they were extremely hard to manage if you weren't taking engine updates. Another one that's kind of really key is like the engine is going to be improving, the tools are going to be getting better, and you don't want your live service team, which may be kind of strapped for resources, in a situation where they're like, wow, I really wish I had all of these tools that let other people be more productive, but we can't because we can't take the engine version. So the last one is probably the most kind of obvious one, which is like, what if you want to port to a new piece of hardware? What if there's just new hardware that needs to be supported? And that tends to be the kind of clincher for a lot of these projects. But I'm saying the other reasons were good as well, and it's something that needs to be considered. So, what's actually required for updating an engine? It's when you want to understand the problem space, you need to understand what you have to do. Well, first thing is you got to merge in all of the kind of code divergences. And if you've been working in a project that has not been taking engine updates for a while, these divergences can get bigger and bigger the longer that you aren't kind of bringing in new versions of the data. And often, if you're sufficiently diverged, it's very hard to kind of give patches to each other. So, you can't even push your changes to the engine team so they can incorporate it for a future release if your code is so different. So once you've done that, you've actually got it compiling, you got to test your game. And so you got to make sure everything still works. But this is one of the things where data resilience comes in, because if you have an engine which is able to sort of deal with earlier versions of the content, you can remove one variable from this. If something doesn't work, and you don't have data resilience, you don't know if the build system broke, or if the code broke, or if it can't understand the content, or whatever. If your engine is able to use exactly the same content as a previous version of the engine, then you can remove one variable from that, and it makes things a lot simpler to manage. So, it's not actually just about the game team here, because the way that you develop your engine makes a big difference to how you can ingest engine updates and how you can manage that technology. So for us, we've been experimenting with this, and this is kind of a picture of like where we were at sort of 5 years ago with Frostbite. We would have a kind of mainline development branch, and when a game team wanted to make a game, they would branch off the engine and they would kind of build their own game line, and that would be where they built their game. And some of the games have like their sort of long-running series is like the sports games have kind of yearly releases. This is a huge simplification of how they actually manage it, but you can kind of consider that they have a sort of long-running series with some amount of like sports-specific changes, and they bring in engine releases as they're published. And for us on the Frostbite team, what we would do is we would develop features in branches, and then we would kind of merge them back into the main line. Now, this is where things start getting a bit complicated, though, because, if a game team wants a feature, maybe they'll cherry pick it in early. So they'll get it earlier than the next release, or they'll have to bring it in and then deal with the divergence there. Or maybe we'll be doing some codev with another game, and we'll have to deal with how we bring that into the main line and then also back into their branch. And so you end up with a situation where there are lots of different sort of lines of code to manage. And what we've been heading towards and trying to experiment with is a different model. So Frostbite is trialing a kind of full trunk-based model where the game lines are essentially at dev. We no longer use branches, and the game teams are either using the same kind of development branch that we use, or they're kind of like a day behind because they've got their own integration tests or something like that. And so we have these game lines that are running right alongside dev, and that's not the case for every game. And especially like we have to consider how games have been working previously, and we still support that, and we'll see what works best for each individual title. But in this situation, we're dealing with cases where the game lines kind of branch just for the release, and then that branch is short-lived and it goes back. And this is something that has a kind of direct price, a direct relationship to the cost of engine updates, because it kind of keeps everyone honest. If a game team is perpetually taking engine updates, then we have to be able to keep the price low, and conversely, they can't diverge as much, so their cost is also amortized. So we've got a single dev line, which means, whatever version of the engine you take is the latest version. It's got everything in it. We've got our games at or near dev, and because they have a single dev line and they're getting engine updates very frequently, it's very easy for them to kind of bring in additional features. And we actually spent some time working with DICE to bring one of their studio lines into near dev. And it's the other cool thing is like changes that are being done by game teams, and they do a lot of great changes to the engine, can be brought back into the engine very quickly. And because there's no divergence to really deal with, or not a significant amount. And it also means that, like, from our side in the central tech group, we can catch issues quickly, prove out our processes and our testing methodologies. And certainly our initial signs seem really good. So this has been a great success so far. I think the last kind of big topic I wanted to talk about was that of team changes. So, you have to consider the team makeup, and I talked about this as like a sort of generalized development flexibility and production support earlier. But, you have to be realistic. Like, after the game is launched, some of the team will be moved onto another project. And because of the nature of how pre-production works, you will probably end up with a disproportionately large number of programmers moving. So your engineering capacity will decrease in the remaining team. But it gets more complex than that, because the remaining team is then going to be most likely split up into different groups. So I said previously that, it's not built by a single development team. You may have multiple feature teams running in parallel. So, for example, you could have two teams that each have a 12-week dev cycle, releasing kind of staggered updates, and that gives you a kind of 6-week cadence for updates. And you'll also have another group in parallel working, on hotfixing and maintenance. But the thing that I find interesting about this is data management is still actually the core issue here. You want to be able to support team members moving between teams, because resourcing is very, very hard to plan ahead of time perfectly, at any rate. And, if you have multiple teams running in parallel with some engineering support, you would expect code changes to happen. And you can't have code changes coupled with massive data changes, especially if you want any kind of flexibility. Even the case of just merging things back is going to become super complicated. So, from my opinion, I think what we need to do essentially is just decouple code from data completely, asterisk, in as much as we can, right? So, there are other things that, like, this isn't just, hypothetical, like we can look at mobile and how that worked. So, in FireMonkeys, we wanted to try to avoid using source control branches, because that allowed you to isolate kind of code and data changes together. So you would end up with, like, incompatible data and code that needed merging. And so what we started doing with quite a lot of success was we basically went with a model where all code goes into mainline. So what we do is just data isolation, and we do data isolation by just not shipping the content that is disabled. So this worked very well for FireMonkeys, and it implies something else though, right? Because if you are dealing with kind of code changes, we talked about like load time fix-ups for data. Why not design time fix-ups? And in fact, we could go a step further. Like, if we're saying we're dealing with live service teams, we're dealing with parallel teams, what about if we bring the kind of concept of patches and the deployment of patches all the way back to the content tools? And so that's our plan. Like what we're currently working on, the kind of initial prototyping for, is really a kind of just-in-time, like non-destructive upgrade system for content, and that works at authoring time in addition to what we've already described at runtime. And changes to the build system, changes to the way we deploy assets that allow us to keep kind of shipped content frozen unless we actually need to change it, and managing the kind of costs associated with that. We then kind of at the authoring tool side, we introduce the kind of concept of data layers and data isolation, basically patches and DLC, or you could construe these as like different A/B tests or something. And we have that fully integrated into the tool. So you have a single code line, but we then have kind of virtual data isolation going on top of that. And then that lets us essentially model the authoring of all kinds of content: patches, expansion packs, DLC, A/B tests, concurrent A/B tests. All of that can be built in a kind of natural way, right at the level of the content authors, without it being something that's kind of built on top of it. So just kind of to conclude, I think like modern games, especially like the live service games, they have different requirements to what we would anticipate we needed to build, say, 15 years ago. And in the case of Frostbite, what was once one of our greatest strengths actually has become a bit of a liability when we deal with these kind of more complicated cases. And this is one of the things where, like, the market has changed and we need to adapt to that. So I think that the other really important part of this, though, is that nothing I've mentioned is exclusive to live service or exclusive to HD or exclusive to mobile. This is all stuff that benefits normal development. Having something where you have better data management, where your data is more robust to code changes, means you can do faster code updates. You don't have to rebuild assets. That's all great. If you have a really kind of strong dynamic content system where you can push additional data to the runtime without having to make it, particularly special or anything like that, that has huge benefits for testing and, trying out ideas. And, better processes for ensuring that you keep divergence low and engine updates cheap. It's also like, it's always good. These are all good things. And, so... thanks for listening. I will be around to answer questions, and hopefully you got something from this. Cheers.